Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the new chapter of network analysis, that is locus diagram. So we will try to wrap the locus diagram within a single lecture. So this will be a long lecture. So sit tight and listen to me carefully. So like you can take a break in between because this might go stretch till 2 and 2.5 hours. So you can take one single break. You may not be able to watch this in one shot. So let's basically start. What is a locus diagram? So as from this figure, I think you can understand. What does locus mean? Locus is the graphical representation of different points. So we are plotting the points. Locus of what? Locus of anything, any quantity. So here in our case, for network analysis purpose, a locus diagram is a graphical representation of how the impedance, admittance or current or any quantity that varies with frequency or some other value, we just plot it in the real and imaginary axis. So once we will see few examples, we will understand. Locus diagram is widely used in network analysis for system design and for control theory. Like if you have heard about the chapter root locus, there what we do, we plot the locus of closed loop poles on the real and imaginary axis of S plane. So that is also a locus diagram only. So generally the real axis generally will consist the resistive component, but it's nothing fixed, it can change as well. And generally the imaginary axis contains the inductive and capacitive. This is just in general, these two things can vary as well. In general, I'm talking here. Okay. So first, obviously, let's start with an example, and from this example only we will understand what is a locus diagram. So given your v of s, it is like a function of s. S is a Laplace domain function. So you ignore that fact. Just in network theory, for network theory, what you have to do, simple replace s with j omega. That's it. Omega is the frequency and j is the complex quantity. That's it. That is the only information that you need to know in network theory. So yeah. So here we have to plot the locus of v of j omega as omega, and omega varies from 0 to infinity. So like the general procedure is to plot with a table. So first you put the table and you put different values of omega. So let's try different values of omega. Let's try for omega equal to 0. Let's try for a fact for omega equals to 2, and then we will try for omega equals to infinity. Okay. So for omega equal to 0, how will the function look like? So the function will be v of j omega equals to 10 divided by j2 plus 2 divided by 5 1 plus j. Okay. This is for omega equal to 2. Sorry, this is for omega equal to 2. First I have to replace with omega. So this I will come to this later on. First let's write it in terms of omega. So this will be 1 by j omega plus 2. Now if I replace omega with 0, this will be simply 10 by 2. Correct? This will be 5. So the value of, what is the magnitude? This is what? 5 angle 0, correct? So magnitude is 5. Magnitude here is 5. What is the angle? Angle is 0 degrees. Okay. So like it has only real component. It only has real component. So it will be lying on the positive x axis. This is my point 5 comma 0 or 5 angle 0. What about the omega equal to 2? If omega is equals to 2, basically it gets simplified like this. It will be 5 by root 2 angle of minus 45. Correct. So the angle is minus 45, but the magnitude also reduces. Basically initially I was here, this was my vector, now the angle is minus 45, so I will go in the clockwise direction. This means what? Rotate in the clockwise direction from the positive x axis with minus 45 degree angle, and this magnitude also has reduced. So now I will be lying somewhere. So initially my phasor was here. Okay, this is wrong, this is not correct. Initially my phasor was somewhere here. Now the phasor is at 45 degrees, and of course the magnitude also has reduced, and ultimately this point is what? This point is 5 by root 2 angle minus 45 degrees. What about the last point? If omega is tending to infinity, what will happen? This will be what? 5 by j omega. Omega is a very very large number, plus 2. So this can be simply ignored, right? This is 10 only. This can be simply ignored. So this will be 10 upon j omega. So if omega is very very large, then ultimately this will be what? This j will go here. So angle will be minus 90. Angle will be minus 90. Okay. But what about the magnitude? Magnitude will be 0. And 0 does not have any angle, so it will be simply 0 only. Okay. So ultimately, right, it comes, my phasor is here. Just to represent, I am showing its magnitude is actually 0, it is actually here, somewhere here. Minus 90, it is tending to minus 90. Angle is tending to minus 90, but it is somewhere here. So actually the locus, I have to point the what? I have to point the points basically. I have to plot the points. I have to plot the points. So my point will look something like this. My point will look something like this. If I plot the locus, it will be not exactly a semicircle. I will prove you it will be a semicircle as well. It will be exactly a semicircle actually. I will prove it to you why this locus is a semicircle. I will prove it to you. Okay. So it will be semicircle. So this was the second point. This was the first point, and this is the last point when omega is infinity. So basically I start from here, from this first point omega equal to 0, and go till omega goes to infinity. That is what they have asked, right? They have asked to vary my omega from 0 to infinity. So this is basically the locus diagram. That's it. That's it. This is the locus diagram, right? And in this locus diagram, they might ask few questions. That's it. That's how simple it is. So first question should be like, this is a semicircle. I will prove it to you why it will be semicircle. First question can be, what is the diameter of the semicircle? So the diameter of the semicircle is simply, if you solve this, let me use some other color. So diameter of the semicircle will be 5 only, right? This will be 5 because the distance from here to here is 5. The radius of the semicircle is 2.5. So this is the locus of v of j omega with respect to omega. That's it. Locus of v of j omega with respect to omega. Okay, that's basically it. So that's how you plot the locus diagram. Now let us come to the proof why is the shape a semicircle. So for that we have to use a bit of mathematics. So what is my v of j omega? V of j omega is 10 upon 2 plus j omega, right? Now let us rationalize this thing. So if I rationalize, this will be 10 upon 4 minus omega square. So 4 minus omega square, this will be equals to, of course you cannot forget here I have 2 minus j omega here as well. So this will be 20 by 4 minus omega square minus j omega divided by 4 minus omega square. Okay, of course 10 is there. This will be 10 omega upon 4 minus 4, not minus, sorry, this will be plus, right? Because a square minus b square, there is j as well, j square becomes minus 1, ultimately it is plus only. So this will be plus, full plus omega. Okay, so now this is basically your x value and this is basically your y value. And what is the equation of a circle? The equation of a circle is something like this, that x square plus y square equals to r square. The most basic equation of a circle, correct? So let us find out this x square plus y square. Let us find out this x square plus y square. So if I find out the x square plus y square, so x square is this 20 divided by 4 plus omega whole square, and what is my y square? Y square is minus 10 omega divided by 4 plus omega square whole square. So this r, right, is a constant, right? This r square is a constant. So we are looking for a constant after this addition. We are looking for a constant. Okay, so let's say if we get a constant or not, this will be for 20, right? This 10 square I can take common outside. Okay, this 10 square I can take common outside, this will be 2 square, that is 4, divided by this 4 plus omega square also I can take common, whole square I can take common. So this will be left with, this will be only left with 4, and this will be left with 10 square I have taken common, so this will be omega square only, and of course whole square is there. No, whole square is individually, right? No. Okay, so okay, something, am I missing something? Omega square is here. Okay, omega square cancels out. Okay, fine, this cancels out. Yes. So okay, yeah, this, right, this is what, this is 10 square, like this whole thing, and one of these will get cancelled, so this will be 10 square divided by 4 plus omega square, omega square. Okay, now this equation was for the case when my center was at 0 0, but there can be this case as well, right? X minus a whole square plus y minus b whole square equals to c square. If you remember here, right, the center was at a comma b, so we will get some equation something like this. So what is this, 10 square upon 4 plus omega square? If you remember, 10 upon 4 plus omega square, so I can write this, right, I can write this as 2 into 10 upon 4 plus omega square, so this is equals to x, so I can write this whole thing as x by 2, I can write this whole thing as x by 2, that is what I can write, correct? Everything is okay, this is, so this is 100, right? Sorry, this is not x by 2, this is 100, right? This is 100, this is 100, so I can write this, right, this 20, correct? So what I can do, I can multiply and divide by 5. So ultimately what will happen is that this will be 100 by 4 plus omega square, that is what I want, and if I take this 5 on that side, it will be equals to 5x. So this value is equals to 5x actually. So my x square, so what I did, I simply did x square plus y square. So x square plus y square, x square plus y square equals to 5x. This is the equation that I get. Now what I can say is that I can write it like this, x minus x square minus 5x plus y square equal to 0, then x minus, this is what, like I can break it down, this will be x minus 2.5 whole square. What I can do is I can add and subtract here, plus minus 2.5, right, 2.5 whole square, to get it in the form of x minus a whole square minus 2.5 whole square. So this will come out to be plus y square equals to 2.5 whole square. Now I hope you are getting familiarized with your form, that is, this is what, this is the same form as x minus a whole square plus y minus b whole square equals to 2.5 whole square. Now is that what we got? So if I just copy and paste this diagram, locus of v of j omega here, so it is telling us, this equation is telling us that we have a circle at what, center, whose center is x equals to 2.5 and y equal to 0. Is that so? Here, right, x is 2.5 here and y 0. Yes, this is the center, right? This is center, and of course whose radius is 2.5. Is its radius 2.5? Yes. Its diameter is 5. Its radius is 2.5. So we have proved. It. No one will prove it. Okay. No educator. No one will prove it. But I have proved to you. Okay. So like it is not always the case that we will get a equation of circle. Sometimes we will not get equation of circle, but sometimes we will. So this is the case where we will. Okay. So basically this is the main locus diagram. We are done. We are done with the locus diagram. But of course there are questions, so we will do that. So the applications of locus diagram are actually in control systems. There we will plot root locus, polar plot, all those things, frequency response, Nyquist plot. So their locus is actually used mainly. In AC circuits we generally plot the locus diagram, locus of impedance, admittance and other phasor quantities which are generally function of omega. We can plot it for other cases as well. So these are the few cases. Okay, first is I have a simple RC circuit and you are asked to draw the current locus diagram for the following circuit under the given condition when angular frequency omega varies and when the resistance R varies. Okay, So let's first solve it for the first case, that is when the angular frequency omega varies. If the angular frequency omega varies, what is the current in terms of frequency? So if I want to vary omega, I have to write the current in terms of frequency, then only I will be able to plot the locus diagram. So current, right, it is a series circuit. I will be equals to V input upon the impedance Z. So V is some phasor quantity, let's assume it for some phasor value V only. Okay, here omega is varying. Omega varying means this one is varying, right? Your supply frequency is varying. If your supply frequency varies, which will vary? What will vary? If your supply frequency varies, that means your capacitance will also vary. Okay, but your resistance will not vary. So this, right, V, I can write some Vm angle 0 in phasor. What will be Z? What will be Z? So Z will be equals to R plus 1 by j omega c. This is the impedance that I am seeing from the source, correct? So now if I vary this, like Vm will not, like phasor quantity Vm will not vary, correct? This will simply be j omega c Vm angle 0 j omega angle 1 plus j omega c. Okay, so this will be what? Basically this will be my I, current I will be omega c is some constant. So here you can do two things. Either you can write the magnitude and phase separately, or you can write in rectangular format. So I will write the magnitude and phase separately now. So what is the magnitude? Magnitude of I will be, this will be omega c Vm divided by under root, okay, omega c Vm divided by under root omega r c whole square plus 1. And what about the phase? Phase of I, this will provide plus 90, this will provide minus tan inverse omega rc. So 90 minus tan inverse omega rc. This is my phase angle. Okay, so we will have a table where we will put the values basically. This is the table actually. One page only it got over. Okay, we will have a table where we will put the values. So this is the table where I will put the values. So for omega, let's take a few cases here. For omega equals to 0, omega equals to 1 by RC, and omega equals to infinity. So for omega equal to 0, what is my magnitude? Magnitude, right? This is numerator is 0, this is finite. So 0 upon finite is 0 only. So at omega equal to 0, my magnitude is 0. At omega equal to 0, my phase is plus 90 because this will be 0 only. So it will be plus 90. At omega equals to 1 by RC, this is 1 plus 1, that is under root 2. This will be what? This will be omega equals to 1 by RC. So Cc will cancel, Vm by R root 2. So this will be Vm by root 2 R. What about the phase? So this will provide how much? 1 by RC means tan inverse 1, is 45 degrees. So 90 minus 45, this will provide 45 degrees of phase. So plus 45 degrees of phase. Okay, plus 45 degrees of phase. What about at omega equals to infinity? At omega equals to infinity, this will be dominating this one. So what will happen? This will like the denominator will only contain omega rc whole square under root. So it will be omega rc. So omega will get cancelled. So at omega equals to infinity, I can roughly write the magnitude equals to omega c into Vm divided by omega RC. So this will be Vm by R basically. Why? Intuitively, can you say this? At omega equals to infinity, what will happen? This will provide zero reactance. So of course, it will become a purely resistive circuit. That's why the current is simply Vm by R. Intuitively also you can understand at omega equal to 0, this will act as an open circuit. So no current will go. So of course, the current is basically 0 because this will act as an open circuit at omega equal to 0. This will provide infinite impedance. So intuitively also you can say, okay, without going into these things, you can say, but the middle value, right, you have to, for this you have to solve. So this omega goes to infinity will provide current to be Vm by R. Okay, and phase will be what? Phase will be 0 degree because it is a purely resistive circuit. Phase also obviously has to be 0. It has to be in phase with the voltage. So initially I am starting with 0 and my angle is somewhere here. So my vector is somewhat like this. Vector is somewhat like this. Obviously magnitude is 0, but it is something like this. It is just going in the positive imaginary axis, correct? Next, my magnitude is increasing and my phase is decreasing. So I am going in the clockwise direction. If phase is decreasing, that means I am moving in the clockwise direction. So I am somewhere here. Somewhere here. Okay. In the 45 degree. This will be large, yeah. So after this, what is happening? My magnitude is becoming maximum and phase is 0. It is positive number, right? Vm by R. So it will be somewhere here. It will be somewhat here. Vm by R. Okay. So it is basically a semicircle, but in the first quadrant. It is basically a semicircle, but in the first quadrant. So this also will be semicircle. You can obviously prove for yourself, but we don't need to prove, and don't worry, no proof will not be asked. So this also will be a semicircle only. Can you tell me the center of the semicircle? The center of the semicircle, this distance, this whole distance is basically how much? This whole distance is Vm by R. This whole distance is Vm by R. And this distance will be what? How much? Basically this will be Vm by 2R. So the center is here. Center is at Vm by 2R, comma 0. Okay, so this is where my center lies. Basically this will be my answer. Okay, I hope you have understood this point. So yeah, pretty straightforward, pretty simple. I hope you have understood the locus diagram, the resistance locus diagram. So let's solve the resistance locus diagram. So if now my resistance is varying, so basically what will vary? Omega is not varying, resistance is varying, so the impedance will vary. The impedance will vary. So this is varying now, right? For the case 2, for the case 2 where my R is varying. So if my R is varying from where? R is going from 0 to infinity. That is what they have given, right? Under conditions, okay. Basically R can go from 0 to infinity. Obviously I cannot have negative impedance for a passive network. So what we can say, again the same thing, what will be the current equation will not change, right? Current equation will be the same, whatever I have derived previously. This will not change actually, this will be same only, all these will not change. Okay, so I will simply copy and paste. I will simply copy and paste because all this will not change, all this will not change, all these will remain same. So what will change? Basically the table will change. Basically the table will change. So here I will vary my R to be equals to, I have to increase the length a bit. Zero, and this can be, what should I vary? 1 by omega c and infinity. So now it is a function of r, because omega is not varying, omega is constant, but r is a variable, r is a variable. So if r is a variable, at r equal to 0, what is happening? At r equal to 0, it is simply omega c into Vm. At r equal to 0, it is simply omega c into Vm, that's it. So it will be c omega into Vm. And at r equals to infinity, how much is the r equal to 0, how much is the phase? Phase is plus 90. So these things are not different, it is same as the previous case only, but now things will change. Now things will change. Now if I put r equals to 1 by omega c, at r equals to 1 by omega c, this is 1, this is plus 1. So how much is the phase? Phase is basically how much is the magnitude? Magnitude is, this is 1. So again it is omega c Vm by root 2. C omega c Vm by root 2. Phase is again plus 45. Okay. Phase is again plus 45. So at infinity, what will happen? At infinity, basically, again, if I break this down, this will be almost equals to, at infinity, it will be omega into c Vm, and the denominator, simply I can ignore the 1, right? This will be omega rc, and this will be omega rc only. Omega rc whole square under root, that will be omega rc only. So ultimately, this is coming out to be the magnitude of I. It is coming out to be Vm by r only. Okay, is it omega is getting, no, not, yeah, ultimately it is coming out to be Vm by r. Yes, if your r is very high, then this quantity will be very high, then I can ignore this one. Now what is r? R is infinity, right? So it is some finite value, Vm is some finite value divided by infinity, so it will be approximately equal to 0 only. So what is the change here? And what is the phase? Phase here does not matter although, but phase here will be, r is infinity, so it will be 90 minus 90, that is 0. Does not matter. Previously what you saw is I started with 0 magnitude, but here as I am varying r, my magnitude is something else, and phase is what? Plus 90. So my vector will be something like this. It will be directly parallel to the y-axis, right? On the y-axis itself, because phase is plus 90. And after, at r equals to 1 by omega c, phase is plus 45, and the magnitude of the vector also has reduced. So I will lie somewhere around here. Okay, and obviously at omega equals to infinity, the magnitude is 0 and phase is of course 0. Phase is 0 and magnitude is of course 0. So just to show you, I will lie somewhere around here. Okay, so my locus diagram will be something like this. It also will be a semicircle only. Okay, but the difference is I will start from here, r equal to 0, and I will end here, r equals to infinity. Again, the diameter of this semicircle will be what? Diameter of the semicircle now has also changed, value has also changed. The diameter is c omega Vm. Okay, and again the center, what is the center? Center is the value, that is c omega Vm by 2. This is the center point. This is the y-axis, right? So 0 comma c omega Vm by 2. This is the center point, and radius is also c omega Vm by 2. So here that was the difference, right? Here the diameter was Vm by r, center was Vm by 2r, and the circle was something like this. So my direction was something like this. I started from 0 degree angle, I started from 0 magnitude, and I went on to the 0 degree angle only, but magnitude Vm by r. Okay, so that is the difference over here. So here this is the value from where I start at omega equal to 0, and this is the value at where I end at omega equals to infinity. Okay, and that in this locus diagram, what is the difference? So arrow has a very high significance, right? Don't, make sure to put the arrows to add a meaning to the diagram. Without arrow, your diagram does not have any meaning. So we start from here, r equal to 0, and we go on till here, r equals to infinity. So yeah, so I hope you have understood this point. So let's now There are a few key properties that I want to discuss about the locus diagram. If omega varies and R is fixed, the reactive components, inductive reactance or capacitive reactance will change, altering the phasor relationship between the current and voltage. So that will change basically. If R varies, then omega is fixed, then the reactive component, that is in reactance or inductive reactance and the capacitive reactance, those will remain same, those will not change. Okay, so basically those will be same. So accordingly your current and magnitude and phase will be varied. So these are the few key points that you need to keep in mind. So again I have a RC circuit, but this time I am not doing the current locus diagram, I am plotting the admittance locus diagram. So now I will solve a bit faster, because you already know how to solve this, right? So this is a series RC circuit, and if I am plotting the admittance, I know for omega equal to 0, intuitively let's understand, this will always be a leading power factor circuit, correct? Because it is capacitive. So basically it is capacitive. If it is capacitive, it will always be a leading power factor circuit, because I am plotting the admittance only. No matter what, it will always be a leading power factor circuit, right? So if it is leading power factor, basically my phi will be positive, basically my theta I will be greater than theta V. Okay, so if phi is positive, phi is what? Phi is the admittance angle only, correct? This I have taught in the previous chapter. So phi is the admittance angle, so admittance angle will always be positive. So basically my phase will always be positive. If my phase is always positive, that means I will lie on the either on the first quadrant only. I can only lie in the first quadrant. Why I can only lie in the first quadrant? Because for a passive network, my R can never be negative, right? R will always be greater than 0. So if R is greater than 0 and the imaginary component, of course, is always positive, that means I will lie in the first quadrant. Okay, for the admittance locus diagram. This first quadrant for the admittance locus diagram, not for the impedance locus diagram. For the impedance locus diagram, it will actually be fourth quadrant. Okay, don't get confused. For the admittance locus diagram, I will always lie in the first quadrant. That I will prove it to you as well. Like we will see as well. Okay, so what is the admittance value basically? So intuitively, this is what you can see. Okay, so in interview as well, this is how you explain. Okay, so without plotting anything. So my admittance, right? What will be my admittance? Admittance will simply be 1 by Z, correct? And Z is basically 1 by R plus 1 by J omega C. So this will be J omega C divided by 1 plus J omega RC. Okay, so this magnitude, what is the magnitude? Magnitude will be omega C divided by omega C divided by 1 plus omega RC whole square whole under root. Okay, this is my magnitude and my phase angle is 90. This provides a plus 90-degree phase and it is tan inverse omega C. Now can you, like whatever you do, the maximum value this tan inverse can give is 90 plus 90, right? And minimum is minus 90. Minus 90 we will never go because this is a positive number. Okay, so this can vary from 0 to 90 only. This will never go beyond 0 to 90. So my phase will always be between 0 to 90. That is the first quadrant. Okay, so this is the case basically. So if I draw the like the locus I will draw now a bit fast. Okay, so here, so I will vary few values basically. So I will vary for omega equals to 0 and infinity. I will directly vary for omega equal to 0 and infinity because I hope you know the middle point. What will be the middle point? So at omega equal to 0, what is the magnitude? This is 0 and this is some finite value 1 plus 0. So 0 upon finite is 0 only. So magnitude will be 0 only. What about the phase? Phase will be 90 only, plus 90. Okay, but it does not matter because if the magnitude is 0, you will not be able to see the vector. Okay, the vector will be somewhere here, but you will not be able to see because the magnitude is plus 90. Okay, what about the omega equals to infinity? For omega equals to infinity, again you will do few approximations. For omega equals to infinity, again this I can neglect. This will be omega RC whole square divided whole under root. So it will be omega RC, omega C divided by omega RC. So this will be omega C divided by omega RC. So this will be 1 by R. Is this intuitively correct? Yes. At infinity, this will provide zero reactance. So it is a purely resistive circuit, and for a purely resistive circuit, what is the admittance? The admittance is simply 1 by R. The admittance is simply 1 by R. That is the admittance for a purely resistive circuit. So this will be 1 by R. What is the phase? Phase, if I put omega equals to infinity, this will provide me 90 degrees of phase. So this will be 90 minus 90, that is 0 degrees. So this will be 0 degrees. So this is on the positive real axis. So on the positive real axis I am lying. So basically I am somewhere here. Okay. So it will be like something like this, right? Something like this. So I am not plotting the middle point. I hope you are understanding the feeling. So somewhat it will be like this. Okay. This will be the semicircle basically. Again the same thing only. What is the diameter? Diameter this time is basically, this is 1 by R. Okay. And the center will be 1 by 2R comma 0. This is the location of the center. That's it. So I start from here, omega equals to 0. I end here, omega equals to infinity. The arrows will be something like this. Okay. That's it. That's how simple the locus diagram is. Okay. This is the admittance locus diagram. Now let's solve for the second case where my R is varying. So this was for the first case where my omega is varying, but it does not matter basically. Like your expression for omega will not change, right? So here my omega is varying from 0 to infinity, and in the next case basically what I will do, I will vary my R basically. I will vary my R. So if my R is varying, what will happen? Everything will remain same, right? This whatever we have calculated, this will not change. This will not change, but ultimately the values that I am putting, that will change. So here now I will vary my R. So R will go from 0 to infinity. So if R is 0, what is the magnitude? Again, magnitude is omega C. Previously it was 0. Now magnitude is omega C. And what is the phase? If R is 0, this is 0, so it is plus 90. So this will be plus 90. If R is infinity, again I can make few approximations. If R is infinity, the approximation will be, again, like this will be purely like resistive circuit only. This will be omega C divided by omega RC. So approximately this will be equals to 1 by R. So approximately this will be equals to 0 only, because R is tending towards infinity. So this will be, magnitude will be 0. I don't care about the angle, but if you want to, you can put here omega R equal to infinity. This will provide you 90 degree of angle. So 90 minus 90 is 0. So overall my angle is 0 only. So again, now the difference is I am starting from the imaginary axis with magnitude of omega C. So this value is omega C. The diameter of the semicircle will be omega C, and I will end on the positive real axis only. It is 0 degree only. Okay, and this is how it will be defined. Okay, now just the central location and the diameter of the semicircle has changed obviously, but still I am in the first quadrant only. Can you notice this thing? I am in the first quadrant only. I told you, right? I will always, for the admittance locus diagram, I will always lie in the first quadrant because it is a RC circuit. So these things you can do intuitively without even solving anything. Without even solving anything, these things you can do intuitively. So from where I am starting? So I am starting from here, that is at R equals to 0, and I am ending here, that is at R equals to infinity. Arrows will be something like this. Okay, and this is the center point, and center point has the value as this, right? This will be omega C. So this will be C omega divided by 2 . Okay, 0 comma C omega divided by 2. That is what this value will be. Okay, so now basically like yeah, these are the few key properties. So here the admittance locus diagram is plotted, conductance is this, resistance is this, how it like varies, how my locus diagram is, that is what is told here. Okay, so the next one is draw the impedance locus diagram for this following conditions. So like what I will say to you guys is try it out by yourself. I will not solve it in front of you, I want you guys to do. So I have done the two, so this one is up to you. Please do it on your own, please do it on your own. And now we will solve the gate POX. Basically this one is the homework for you. I will not solve even in any video, I will not solve. This one is for you, okay, because I want you to do something, and this is the easier one, this is the easier one actually. Okay, so you solve by yourself. So this I will delete, and this, okay, this is fine. Okay, so let's few important points are there. Don't need to remember this. If you know this, that's a good thing, that's a plus point. So the first key point is a first order network with one energy storing element will always produce a semicircle in the complex plane. Locus diagram, I'm talking about locus diagram. A second order circuit with two energy storing element will produce a circle. Okay, so if you know this, this will be helpful. It's okay if you don't know, if you don't remember it, that's fine, you will still be able to solve the questions. But if you know this fact, it will be a plus point for you. So let's solve few gate POI. So I will pause the video, you take the screenshot, like I will not pause the video, you take the screenshot of these questions, and after you try attempt it, you have attempted the questions, I will solve all the questions. So you try to take the screenshot and solve all the questions. So before starting the questions, actually I wanted to explain that diagram as well, this one as well. So like impedance, you will be able to solve. Basically this will be r divided by 1 plus j omega, that is the impedance, right? So if I take this j at the top, the magnitude will be r square plus 1 omega c, and the angle will be what, this is in the which quadrant, this is in the fourth quadrant, so angle will be minus tan inverse the imaginary upon the real, so that is 1 by omega rc, that is fine. But at omega equal to 0, something unusual is happening, that is we are not getting a semicircle anymore. Okay, we are not getting a semicircle, we are getting infinity. So that's why I thought that I should actually explain this one. So at omega equals to 0, what am I getting? At omega equals to 0, my magnitude is infinity. Why? Because if you put omega equal to 0, this is constant and this is 1 by 0, finite upon 0 is infinity. So ultimately your magnitude will be infinity. But what is the phase? At omega equal to 0, this is tan inverse infinity. And what is tan inverse infinity? It is 90 degrees. And a negative sign is there, so it will be minus 90 degrees. What about omega equals to infinity? At omega equals to infinity, this will tend towards 0, so this will be r only. This will be r only, and your angle, this will tend towards 0, angle will also be 0 only. Okay, now intuitively can you understand this? Intuitively can you understand this? Yes, right? So if your omega is 0, basically if omega is 0, this is infinity, this is providing very high reactance, so this will dominate over the r, so it will be a capacitive circuit, purely capacitive, and purely capacitive circuit has a phase angle of minus 90. Okay, that's why. And if omega is infinity, this will be almost short circuit, so there is no capacitive reactance, only resistance is there, so it will act like a purely resistive circuit. And for a purely resistive circuit, the impedance is r and phase shift is 0. Obviously for a purely capacitive circuit, as omega is to 0, so 1 by 0 is infinity, that's why the magnitude is infinity. So how will the phasor look? So not for phasor, sorry, how will the locus diagram look? Locus diagram will be in the fourth quadrant always. Locus diagram will always be in the fourth quadrant. Locus diagram of what? Locus diagram, remember always, whenever you are drawing the locus diagram, you should remember in your mind, in your head, that this is the locus diagram of what? Locus diagram of z of omega, that is the impedance. Impedance locus diagram. Okay, so it will be somewhat like this. So I will start from infinity. Of course, I will not be able to show infinity, so I will be starting from somewhere here, omega equal to 0, and I will end here, omega equals to infinity, and I will move like this. Why it will be a straight line? Why will it be a straight line? Why will it be a straight line? You might have a question, why is it a straight line? Why it is not like this? It is a straight line because if you observe in this z, right, this is the real portion and this is the imaginary portion. In this z, this is the real portion and this is the imaginary portion. Here the real portion is constant, just the imaginary part is changing, that's it. The magnitude of the value of the imaginary part is reducing, but the x coordinate is constant. That's why here the x coordinate is constant, the distance from the y axis is constant, that is r. Okay, previously if you would have focused that my expression was not very simple, right? Here my real and imaginary part both are function of omega. Here as well previously, if I just show you, this was also both omega. Here as well, if you see, your real and the imaginary part both are function of omega. But in this case, actually real part is independent. It is not varying at all. Real part is independent, it is not varying at all, it is constant. So x equal to, basically this is the line x equal to r, where here y is varying what? Y is equals to minus 1 by omega c, that's it. This is the equation of the line basically. Okay, so this is constant and you are varying the omega, hence your y is varying. Okay, so what about the next one? Okay, let me copy and paste this thing. Let me duplicate. Okay, let me add it here. So this will not change, right? This will not change. But now the second case is I am varying the r from 0 to infinity. R is the variable. In the first case, I was varying the omega from 0 to infinity. So here, this expression will not change, right? This will remain same. What will change now? All this will change. Now, if you notice, you don't even have to write the angle and phase or for all those things. If you notice, your r is varying, your omega c are a constant. So this time, your imaginary part is constant and your real part is varying. Your imaginary part is constant and your real part is varying basically. Have I missed a table here? No, like it should be there. Okay, it is not there for some weird reason. It is not there. Okay, so what I can say is this time my real part is varying, so this will vary, and imaginary part is constant to what? Minus 1 by omega c. So y is equals to minus 1 by omega c. So it is somewhat negative here, and this is always present, right? This y value will always be at 1 by omega c. X value will vary. From here, no, x value can never go negative, right? Because it is a resistance. It can start from 0 to infinity. So basically, your value will be something like this. Okay, here this will start from omega equals to, not omega, r equals to 0, because at r equal to 0 x is also 0, and it will go on till r equals to infinity. When r goes to infinity, x is also infinity, right? But your y value is always constant. Y value is constant. Y is constant, that is minus 1 by omega c. So that's how simple it is. Okay, so this was just a new thing that I did not mention in the previously, like we were only getting semicircle. So yeah, that might like this is a new thing, so I think you should take the learning from this. So let's solve few questions. So this is the first question, where I have a series RC circuit and that is excited with 1 volt AC source. The locus diagram of the phasor current I will be what? The locus diagram of the phasor current I will be what? As C is varied. So basically I have a series RC circuit. Okay, so I have a series RC circuit. This is my series RC circuit, and what are they varying? And it is connected to a source of 1 angle 0, sinusoidal source of 1 angle 0, RC. So they are asking me to plot the locus diagram. So we have already done it actually, as the C is varied. C, now we have varied omega, but we have not varied C. So if I vary C, if my C is 0, what will happen? If my C is 0, what capacitive reactance will it provide? 1 by 0. 1 by 0 is infinity. So if it is providing infinity capacitive reactance, so it will behave as a purely capacitive circuit at C equal to 0. So at C equal to 0, it will behave as a purely capacitive circuit. That means my current will be purely imaginary. My current will be purely imaginary. Current will be leading the voltage by 90 degrees. So angle of current will be 90 degrees. Correct? I will not do any calculations. Without calculation I will solve. So angle of current will be 90 degrees at C equal to 0, because it will be a purely capacitive circuit. Why? Because the capacitive reactance is 1 by omega c, that is the reason. Okay, so if it is 1 by omega c, so at c equal to 0, angle will be 90. What about the current magnitude? Current magnitude actually will be 0. Why? Because impedance or the capacitive reactance is tending to infinity, so of course current is voltage upon reactance or impedance. It is, for this case it is purely capacitive, so it will be 0 only. So I will be at 0, so that is fine. Everything starts from 0 only, that is fine. But what about the other case? Now one thing I have told you, that it is a capacitive circuit, right? RC circuit. So in RC circuit, the behavior can only be leading. The behavior, whatever you do, behavior will always be leading. If it is leading, that means the current leads the voltage. So angle of the current will always be positive with respect to the voltage, because voltage is the reference. They have given the voltage as the reference, correct? So as it is a leading circuit, RC circuit, it will always be a leading circuit. Now as it is a leading circuit, it will always be like basically your, what do you say, your angle will always be positive. If it is positive, that means I will always lie in the first quadrant, because for a passive circuit angle can vary from minus 90 to plus 90. If it is positive, that means I will only lie in the 0 to plus 90 range, so I will always lie in the first quadrant. So I can directly eliminate all the options. My option A will be correct. Option A will be correct. Or if you want to do analysis, you can of course do the analysis, like you can solve for the current value. Current is V by R plus 1 by j omega c, and solve. Okay, this is the method 2. The method 1 was basically with induction, and this is the simple analysis, numerical analysis, and this is with the induction. You can solve. I have already solved, right? RC circuit I have already solved, so I will not solve. So let's solve this question. So in this question, a fixed capacitor with reactance of minus j 0.02 is connected in parallel with a combination of a fixed inductor and a variable resistor. So I have a capacitance, okay, which is 0.02 ohms, and I have a inductance and a resistance. Resistance is varying, inductance is fixed to j 0.01 ohms. Okay, so what can I say? What can I say? So I can say basically the, like, what are they asking? They are asking the admittance locus diagram for this circuit. What will be the admittance locus diagram? So admittance is from here. So admittance, right? How will I in when things are in parallel, admittance simply gets added, correct? Admittance simply gets added. So the admittance will be 1 by R plus j 0.01 plus 1 by minus j 0.02. I hope you understand, right? I hope you understand that admittance simply gets added when the things are in parallel. So this whole circuit, what is the equivalent value of this circuit? What is the equivalent impedance of this circuit? J 0.01 plus R. What is the equivalent impedance of this particular circuit? Minus j 0.02. So if things are in parallel, simply their admittances will get added. What is the admittance? It is the inverse of the impedance. What is the admittance of this? Inverse of the impedance. Got it? So this will be, if I like simplify this thing, this will come out to be R minus j 0.01 divided by R square minus 0.01 whole square. This will be plus only, not minus, sorry, and this will be plus j50. Okay, so basically both your real and the imaginary portion are varying here. R square plus 0.01 whole square minus R square into 0.01 plus G50. Okay, So from here, basically what you can do, you can vary your R, because they are varying the R, right? Because R is a variable. So if R varies, what is the admittance locus diagram? That is they are asking. That is what they are asking. So let us plot the admittance locus diagram. So this will be my admittance locus diagram. Okay, so this is basically the real part of my admittance, and this is the imaginary part of my admittance. So I hope you remember, like I'm not explaining what is real imaginary. I hope you know how to plot real and imaginary portions, right? So that's why I did not waste any time explaining these things. So because I told you already, I hope your basics of complex numbers are already cleared. So at r equal to 0, what is happening? At r equal to 0, this is 0. At r equal to 0, this is not 0 actually. At r equal to 0, what is this? So at r equal to 0, omega, y at r equal to 0 is basically, this is 0 minus j 0.01 divided by 0.01 whole square. Okay, so this cancels out, so it is 1 by 0.01, so it is basically 100 j minus 100 j plus j 50, so it will be minus j 50. So my y value is at minus j 50, so I will be lying somewhere around here. Minus j 50 is here, right? 0 comma minus 50. This will be the point at r equal to 0. Okay, what about at r equals to infinity? So right, you don't always have to use a table. With a table also you can solve, right? Simply write the real and imaginary part. That's it. Without table also you can solve. So there are multiple ways to solve a single question. I did not explain to you like this one, right? Just write the real portion of the y and imaginary portion, and from there also you can plot it on the graph. Angle also you can do, magnitude also you can do, or real or imaginary also you can do, whatever suits you. So at r equals to infinity, what is happening? This one will dominate than this, so it will be r by r square, so it will be 1 by r basically. So approximately it will be 1 by r. Okay, what about this one? Again this one will dominate over this, so approximately this will be 0. Minus j 0.01 divided by r square, plus j 50 is a constant number. Of course r is tending towards infinity, so of course this will be 0, this will be 0, so ultimately it will be plus j 50. So this value is plus j 50. At r equals to infinity, this value is plus j 50. Okay, that is 0 comma 50. So this is fine, but it is semicircle, because certainly it is like a, okay, I cannot certainly say it is semicircle. I cannot certainly say if it is semicircle or not. I cannot comment about that, right? I cannot comment about whether it is a semicircle or not. So what you can do is you check the angle. Can my angle ever go like here? There are 4 options, so you have to go with the options as well. Here they are telling a semicircle, a straight line. Which is the case? Straight line, right? Straight line happens when either my imaginary part of the locus, whatever I am plotting for, imaginary, or the real part is fixed. Okay, now is that the case here? Is my real or imaginary portion is fixed? No, imaginary part is also a function of r, real part is also a function of r, so it is not fixed. So this is not possible, this is out of the picture. Now these are the only possibilities. So first one is telling a semicircle with diameter of j 100 and centered at origin, a semicircle with diameter of j 50 centered at origin. So if it is a semicircle, right, I have to connect these points. So either they will be connected through here or here. Now I know they will be connected like this. Why? I will explain, just in a second I will explain. You will also say, sir, okay, now I know why it is connected like this. So if it is a semicircle, for certain from the options I can say it is a semicircle only. So I will start from here and I will go till here. So if it is a semicircle, now if I have connected, can you tell me the diameter of the semicircle? Diameter of the semicircle is 100. Diameter of the semicircle is 100. Diameter of the semicircle is 100 basically. So diameter of the semicircle is 100, okay, and isn't that they are asking? Yes, diameter of J100, yes, that is correct, because it is in the y axis, so that's why they are telling it is G100. So it is correct. So this option is correct, right? Option A is correct. Now diameter cannot be J50 because I have to connect these 2 points. If I connect these 2 points and this is a semicircle, it cannot be J50 because J50 is only here only, this much distance, right? So it is the radius, it is not the diameter. Now why am I on the right hand side of the imaginary axis and not on the left hand side? I am on the right hand side because from the real, if I see, the real part is always greater than 0. The real of my admittance is always greater than 0. If the real of my admittance is always greater than 0, basically I will lie on the right hand side of my complex plane. So that's why basics of complex number is also very, very important. That's why we have focused so much in fundamentals. How is my real of y always positive? Here, right, it is r square. So r square, r is a real quantity, resistance is a real quantity, r square will always be positive. This is always positive. R is a positive quantity. I cannot have negative resistance in passive linear network. If it was the case, they would have mentioned. So again, this whole thing is positive always. This is the imaginary part. Imaginary part I don't care, but real part I can certainly say it will always be positive. So I will always lie on the right hand side. So I can say here as real of y is always positive, I will my locus diagram of admittance will always be on the lie on right hand side of imaginary of admittance. Okay, so this was the basic point. So we have two more questions. We have two more questions actually. So this is the next question. So in this question, what we have to do, we have been given as RLC circuit. Okay, RLC circuit is given, supplied from a variable frequency source. So we are varying the omega, and what are they asking? The admittance locus diagram of the across the AB terminals. So AB terminals, sorry for not providing, AB terminals is actually here. This is A and this is B. Basically, it is a like the admittance of RLC only. So admittance locus diagram of RLC. So intuitively, can you solve? Intuitively, can you solve? So at omega equal to 0, what is happening? This will be open circuit, because this will what is the capacitive reactance? 1 by omega c. This will be open circuit. This will be short circuit. This will be short circuit. So what is the admittance? Admittance will be dominated by this one only, right? In a series circuit, whichever has the highest value, that will be dominated. So at omega equal to 0, my behavior is capacitive. My capacitive behavior, I have a capacitive behavior. If I have a capacitive behavior, what are they asking? Admittance locus diagram. So what is the admittance angle? What is the admittance angle? Admittance angle is the theta I minus theta V. Correct. So if it is a capacitive behavior, that means it is a leading circuit. If it is a leading circuit, that means my current will lead the voltage. That means theta I will be greater than theta V. That means theta I minus theta V will be positive. That means my admittance angle will be positive. My admittance angle will be positive. Now if my admittance angle is positive, that means I can lie on the first quadrant. I will never go in this left hand side of the imaginary plane. Why? I may go in the left hand side. No, I will never go in the left hand side of the imaginary plane. I will also prove it to you. I will also prove it to you that I will never touch the left hand side of the imaginary plane. Okay, that will never happen. That will never happen basically. Why? Because it is a passive linear network and my conductance will not be negative. It has to be positive. So as my conductance is not negative, this is cancelled out, this is cancelled out. Only these are the possible cases. So in these two cases, one is saying I will go in the anti-clockwise direction, one is saying I will go in the clockwise direction. Whom I will believe? Whom I will believe? So let's take for the case they are asking admittance, right? So if they are asking admittance, so at omega equals to 0, okay, so at omega equal to 0, what is the admittance basically? At omega equal to 0, I told you this will be dominating, correct? Because 1 by omega c is there, this will obviously be dominating. This will obviously be dominating. All this will go away because 1 by omega c has the highest impedance. In series circuit, we see the impedance. We see the impedance. In series circuit, we see the impedance. So let's say I have a number like this Zn. Zn is here R plus j omega L plus 1 by j omega c. Now if you put omega equal to 0, omega tending to 0, this will be gone. Okay, this will be finite upon 0. So very high number plus R, that is a finite number. Infinity plus finite is infinity only. So I will only consider the omega. So my impedance roughly will be equals to 1 by j omega. See, my impedance roughly will be equals to 1 by j omega c. What will be the admittance? Admittance will be j omega c. What is the angle of the admittance? Plus 90. What is the value of the admittance? 0. Because obviously you are making omega equal to 0. If you are making omega equal to 0, omega c will be 0. So value of magnitude of the admittance will be 0 and angle will be, admittance will be plus 90. Okay, but as it is 0, we don't care. So we will start from here. That is for certain. We will start from this point only. Where I will go next? Will I go in the top side or bottom side? So if you see, if I am reducing my admittance, what is happening? Sorry, if I am increasing my frequency, as frequencies increase, what this one will reduce, but still this one will be dominating, right? Why? Because let's say my L, let's take an example value, L is 0.1 and omega is 0.1, okay, and C is also 0.1. So what is happening? This is omega L is 0.1 into 0.1 plus 1 by 0.1 into 0.1. Still it is very large. If you see 1 by 0.1 into 0.1 is basically 100 minus j 100 and this is just plus j 0.01. So who will dominate? Still the capacitance will dominate, right? If capacitance is dominating, that means my angle of admittance will be what? Positive. If angle of admittance is positive, that means in which quadrant I will lie? In the first quadrant. Angle is positive. If angle is positive, that means I will lie in the first quadrant. Very simple, right? Very simple. So your answer will be this one, option A. Of course, there is like intuition I have told you, and this is what you will get at PrepFusion. In PrepFusion, you will always get the intuition. Of course, there is very huge calculation. I will show you the calculation. So what you do, like this was the method 1 with intuition. So method 2 is simple calculation. I will obviously not do the calculation, that I will leave it up to you, but I will tell you how to do the what are the values that I will get. So admittance is what? This is a series RLC circuit, so it is 1 by Z. So Z is what? Z is R plus j omega L plus 1 by j omega C, or you can write this as j omega C divided by j omega RC plus omega square LC jj, okay, j square, so this will be minus omega square LC plus 1. So this will be your admittance basically. Okay. So now your calculation will be very complex. So I will show you the calculation basically. This will be if I take the rationalization. If I do the rationalization, this will be 1 minus omega square LC plus omega RC whole square into 1 minus omega square LC minus j omega RC. Okay, so this, right, this point will come out to be, the real portion will be omega square R C square, omega square R C square omega square LC plus omega RC, okay, and okay, okay, so this value will be plus j omega c 1 minus omega square LC divided by, like, I think you're understanding how difficult is the calculation, okay. So now if you vary the omega, you will see how is your like angle varying. So if you put omega equal to 0, you will find some other angle. If you put omega equals to 1 by under root LC, so you put omega equals to, like, you will put 3 points. One point you will put omega equals to 0, another point you will put omega equals to 1 by under root LC, another point you will put omega equals to infinity. For these three cases, you just find out the phase, the magnitude of y, and the phase of y. You will get the same result, you will get the same answer. So like this is a big calculation. So that's why intuition is important, okay, to understand the circuit. I don't, I hate you memorizing stuff. I hate like telling you to mug up this one, but I tell you to have intuition. So this is the last question that we will solve basically. So when the angular frequency in of omega is in the figure is varied from 0 to infinity, the locus of the current phasor I2 is given by 1. So we have to find out the locus of the current phasor I2 with respect to frequency omega. As omega is varied, what is the locus of the I2? So if omega is 0, again this will provide capacitive behavior, because this will be what, 1 by omega c. So again this is a series circuit, so 1 by omega c will dominate. So overall this will be 1 by omega c, overall this will be capacitive only, overall again this will be capacitive, like this is resistive only, and I have a parallel RAC circuit. So overall the behavior of the circuit will be capacitive. If overall the behavior of the circuit is capacitive, basically with omega the angle of current will lead, right, because behavior is capacitive only, so like it will lead only, okay. What about the next part? Next part is, if my omega is increasing, the capacitive behavior will go down. So from leading it will totally be going towards resistive, because when my omega will be infinity, basically this 1 by omega c will vanish, this will be 0 only, so it will be a purely resistive circuit. So my angle somewhat my angle will start from a leading behavior, then it will go to unity power factor, okay. It will start from leading, then it will go to leading power factor, that's it. So this is how it will go. So if I check here, these are the like locus diagrams, okay. These are the locus diagrams. So this is at omega equal to 0. So at omega equal to 0, this is providing infinite impedance, so no current will actually flow through here, all of the current will flow through here only. Why? I have two circuits, one is providing open circuit infinite impedance, other one is providing some finite impedance. Current chooses the least resistive path, so current will choose this, current will not go through this. So I2 will be 0 at omega equal to 0, I2 will be 0. So at omega equal to 0, I2 must be 0, in these two options I2 is not 0, so not possible. B and D, C and D are automatically eliminated, I2 will be 0. Now I2 has to lie in the first quadrant. Why? Because I told you it is a capacitive behavior. If it is a capacitive behavior, then of course current, right, will lead the voltage. This is the point where the difference is voltage, right. So current theta I will be greater than theta V, okay. So current will lead the voltage, so I will lie in the first quadrant. So first quadrant will be here for option A, for option B it is automatically eliminated. This is how we solve using intuition, okay. Of course if you want to solve using the lengthy method, you can solve obviously. So I can directly write, I can take this circuit, okay, I can copy this circuit and I can write down the expression for I2 in frequency domain. So the I2 current, right, okay, this is not 16 volts, What did this 16 volt came from? The I2 current is equals to what? I2 is equals to, this is my phasor E angle 0, EM angle 0, current divider, right? Simple current divider is happening. So opposite upon the total sum, that is R1 plus R2 plus 1 by J omega C. This is my I2 current basically, correct? So this will be basically, they have asked us to plot I2, right? Yeah. So basically this will be EM angle 0, this will be J omega C R1 divided by J omega C R1 plus J omega C, like I can write this like this, J omega C R1 plus R2 plus 1. Okay, so now if you put omega equal to 0, you will see this is basically 0 only, I2 is 0. If you put omega equals to infinity, what will happen? This will dominate over this one. So ultimately, if omega is tending towards infinity, what am I getting? I2 is J EM 0 omega C R1, and of course I can ignore this plus 1. So roughly this will be equals to J omega C R1 plus R2. So it will behave as a purely resistive circuit. So what will happen is this J and J will get cancelled, and this omega C will get cancelled. Ultimately your value I2 will come out to be, it will just be a purely resistive circuit, current divider. So it will be EM phase 0 R1 divided by R1 plus R2. Is, let's do a quick sanity check. Is it correct? So at omega equal to infinity, basically this is acting as a short circuit. So this R1 and R2 are in parallel. Simple CDR you apply. If you apply the CDR, I2 will be R1 divided by R1 plus R2 into the voltage, obviously. Okay. No, right? Okay, something is wrong. Omega C. Okay. Something is wrong actually. Should not be. Okay. Have I done something? Okay. One mistake, one slight mistake, slight error I have done. This right current is not, I can simply not use the CDR here. So this right will be simply I. This is not actually, this is my mistake. This is my mistake here, right? I cannot simply do the current division. So this is voltage, right? Okay, we did not even have to do the current division. Sorry, I'm really sorry. We did not have to even do the current division. I'm really sorry. What I was doing, what I was thinking. So basically, right, this voltage is same across both. This is not a current source, right? I also, like, this type of mistake you will also do in exam. So don't make this mistake. So this is a voltage source. So whatever the voltage here, same voltage is here. So simply it is the voltage upon the impedance. So I don't even need to do the CDR. So it will be voltage upon impedance. Impedance provided by this voltage source is this one. Impedance provided by this voltage source is this one, R divided by J omega. So this is the value. So we don't even have to do that much of a complex calculation. This will be omega C R2, omega C R2 plus 1. That's it. So at omega equal to infinity, basically what will happen? Omega C will be eliminated. Omega C will be eliminated basically. This will be, there will not be any R, so this will be basically EM by R2. Pretty straightforward. It will behave as a purely resistive circuit. Okay, I'm really sorry for that mistake because we almost have ended our locus diagram. That's why I was really tired. So yeah, that's the basic thing. Basically it will act as a purely resistive circuit. So it will be some constant value EM by R2. So EM by R2, if you see, is here. This is EM by 2 R2, this EM by 2 R2. It will, at omega equal to infinity, I should get plus EM by R2. This is telling me at omega equals to infinity, I am getting what? J, phase of 90 degree EM by 2. No, there will not be any phase with the voltage. As it is a purely resistive circuit, it will be in phase with the voltage. So this will be EM by R2. Option A will be the correct answer for this question. So this is the summary. Don't need to remember this. Okay, just whatever method I have told you, that is enough. This is just for good proper notes, and obviously our competition does it, so we have to do it. But I will not tell you to remember this. Just know few things. That's enough. That's enough. So that's it basically for this lecture and for locus diagram. And from next lecture onwards, we will start a new chapter, that is complex power. That is a very interesting and very not complex power, sorry, resonance. We'll start a new chapter, that is resonance. That is the most important chapter for both EC, EE and IN. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.